In this video, we're going to talk about how to differentiate logarithmic functions, and at the end, I'm going to go over a few AP-style questions as well. To find the derivative of a logarithmic function, we start with the fact that y equals log base a of x if and only if x equals a to the y. So those two statements are equivalent, meaning those two functions are inverse functions. So we're going to take the derivative of x equals a to the y with respect to x. So the left side's pretty simple. It's just 1. The right side is an exponential function, and we know the derivative of that is going to be natural log a times a to the y, and then we have to use implicit differentiation times dy dx. Then we solve for dy dx, and you would have dy dx equals 1 over natural log a times a to the y. Now, if we remember a to the y is equal to x, we can back substitute that in, and you get 1 over natural log a times x, or sometimes you might see it written as 1 over x natural log a. Now, an interesting point is that if the base of the logarithm is e, so let's say y equals natural log or log base e of x, which is equal to natural log. If we use this formula, then y prime is going to be 1 over x natural log of the base, which in this case is e. Now, natural log e is just 1, and you get 1 over x. And that is the rule for the derivative of natural log. At the end of the day, we know that if y equals natural log x, then y prime equals 1 over x. If y equals any other base logarithm, so log base a of x, then y prime is equal to 1 over x times the natural log of whatever the base is. We want to differentiate each of these functions. So in this case, we have natural log x quantity squared. You may see this is similar to how they do it in trig functions, written as natural log squared x. Same kind of notation. So y prime is equal to, we have to use the general power rule here. You bring the 2 down times natural log x, technically to the first power, but you don't really need to write that, times the derivative of the inside 1 over x. Cleaning that up, you get 2 natural log x over x. Part B, if we take the derivative, so we have y prime equals 1/2 times log of x. Now remember, if it's just log of x and no base is written, it's understood to be the common log, which is base 10. So this would be 1 over x natural log 10. And then we could just rewrite that as 1 over 2x natural log 10. So for part C here, we assume y is a differentiable function of x and use implicit differentiation. So the derivative of both sides of the equation would be 1 over x plus y prime over y equals 2. And then we would have to solve for y prime. I would subtract the 1 over x to the other side and have y prime over y equals 2 minus 1 over x, and then multiply both sides by y. So y prime equals y times 2 minus 1 over x. For this last one here, or part D, to take the derivative, we can do it in one of two ways. First, we can use the chain rule where we let u equal x cubed, and then this would become y equals log base 2 of u. So dy dx is 1 over u natural log 2 times u prime. And then if u is x cubed, u prime is 3x squared. And we could back substitute everything, 3x squared over x cubed, natural log 2. And then you could reduce the x's and get 3 over x natural log 2. The second way to do this is first apply the power property to the logs. Since the exponent of 3 is on the x, we can bring it in front, 3 log base 2 of x. And then taking the derivative, we would have 3 times 1 over x natural log 2. It's the same thing. You get 3 over x natural log 2 like we did before. Now, in this couple of examples here, we're going to have to use the quotient rule and the product rule. So for part A, if we want to find the derivative, we would have to use the quotient rule. Derivative of the top times the bottom minus the derivative of the bottom times the top all over the bottom squared. Now this simplifies the 1 over x times x simplifies to 1. So this would be 1 minus natural log x over x squared. Second one here, use the product rule, y prime equals derivative of the first times the second plus the first times the derivative of the second, which is 1 over x. And then this simplifies to 2x natural log x plus x. So in G, I want to show you this one in 2 different ways. The first thing we could do is let u equal the root of x. And then u prime is going to be 1 over 2 square root x. So then y prime is u prime over u, following the rule. So 1 over 2 root x all over root x. And then if I make this into a fraction, multiply by the reciprocal, you would end up with 1 over 2 times square root of x squared, which is just going to be x. Okay, I'll show you the other way to do that. So I left our previous answer down there. Again, we could rewrite this square root as a 1/2 power and then apply the power property. So this would be 1/2 natural log x. Didn't do any calculus yet. And now I can take the derivative. Y prime is 1/2 times the derivative of natural log 1 over x. And that's still 1 over 2x. You get the same answer either way. Now part H, we have natural log absolute value of x. So what we can do is express the absolute value as a piecewise function. What I mean by that is natural log absolute value of x is going to be equal to natural log x if x is greater than 0. And it's going to be the natural log of negative x if x is less than 0. Because remember, you can't take the natural log of a negative number. But if you have the absolute value on, you can put any non-zero number in. And it's either going to be natural log of what x is if x is positive, or natural log of the opposite x if x is negative. So then if I differentiate this, we'll set this equal to y, and then say y prime equals 1 over x if x is greater than 0. And then for this second piece, we're going to have to do the chain rule. U prime, which is -1, over u, negative x, which simplifies to 1 over x also, even if x is less than 0. So we can write this as the derivative of natural log absolute value of x is equal to 1 over x. So this leads us to a very interesting problem that can sometimes come up, is where you have natural log of a function that involves all kinds of crazy stuff. So in order to attempt this one the way it's written, you would have to use the chain rule, quotient rule, and product rule. But because it's all inside of the natural log, we can simplify it, or expand it rather, using the properties of logarithms. So not doing any calculus yet, the numerator, since it's a product, can be written as natural log of 2x minus 1 cubed plus natural log square root 2x to the 4th plus 1 minus natural log x. Then we can further simplify this using the power property. In the first term, the 3 can come out front. The second term, the square root, is really the 1/2 exponent, so that can come out front. And natural log x stays. Now notice I didn't do any calculus yet. All I did was algebraically simplify this. Now we can take the derivative, y prime. So this first term would be 3 times u prime over u, so 2 over 2x minus 1, plus 1/2 times u prime over u, which is going to be 8x cubed, and then minus 1 over x. Also, this can be simplified to there you go. Now it's time for some AP style questions. This one's really interesting. If y equals tangent u, u equals v minus 1 over v, and v equals natural log x, what's the value of dy dx at x equals e? Oh boy, so y equals tangent of u. Now, the difficult thing is u is linked to v because u is a function of v, but v is also a function of x. So if we want to take the derivative of y with respect to x, this is going to be the derivative of tangent, which is secant squared u times derivative of u with respect to x. Now u is equal to v minus 1 over v. So du dx is equal to 1 plus 1 over v squared times dv dx. Now, v, we know, is equal to natural log x. So dv dx is equal to 1 over x. So here's what we have to do. We have to back substitute the 1 over x in for dv dx and the du in for, or du dx in for du dx. So this is going to be secant squared times 1 plus 1 over v squared times 1 over x. Now, if x is equal to e, we could substitute that in the 1 over x for e. But the problem is the other two factors are in terms of v and u. Well, right here, if x is equal to e, then v is equal to natural log of e, which is just equal to 1. And then if v is equal to 1, then u is equal to 1 minus 1 over 1, which is just 0. So we would have secant squared of 0 times 1 plus 1 over v squared, since v is equal to 1, it's just 1, times 1 over e. Now, this simplifies. Secant of 0 is just 1, so 1. 1 plus 1 over 1 is 2, so 1 times 2 times 1 over e is going to give us 2 over e. So for this one, the slope of the tangent line to the graph of y at x equals -1 is, so the slope of the tangent line should be a phrase that you recognize to mean the derivative evaluated at the x value. So dy dx equals u prime, so -1, over u, 1 minus x. All right, I'm using the 1 minus x as u. So if I evaluate this at x equals -1, this is going to equal 1/2. All right, so let f of x equal natural log x and g equals arctan root x. The line L is tangent to the graph of f at x equals 2. For what value of x is the line tangent to G parallel to L? Notice we can use Desmos for this one. Key point here is that G and L are parallel. That means their slopes are the same. And we know the point of tangency of f is at x equals 2. So basically we're saying f prime of 2 is going to be equal to g prime of x, but we got to figure out the x value. So let's hop on over to Desmos and figure this out. So here we have natural log and arctan root x. We have to first evaluate f prime of 2, which is 0.5. So I'm going to graph the line y equals 0.5. And notice it tells me where it intersects the arctan function. But that's not going to be our answer because we want to know where the slope of g is equal to 0.5. So I'm going to graph g prime, and then I'm going to turn these other two functions off for the time being, just because I want to simplify what I'm looking at. So here is the point, and it's at x equals 0.46557. And I could double check that by doing g prime of that value. And notice it's really close to 0.5. That's because this is a decimal to 5 decimal places of accuracy. So we would report our answer as x equals 0.46557. Well, that's it for differentiating logarithmic functions. I hope that was helpful to you. Leave me a comment below, let me know what was most helpful, and give this video a like, and make sure you subscribe for when I post more videos.